Welcome to this talk. My name is Reinhold Preiner. I'm with the Graz University of Technology and I'm happy to present today our work on augmenting node link diagrams with topographic attribute maps. Imagine you have a dataset containing some entities and these entities have logical relations to each other. So what you effectively have is a graph, and a typical representation for such a graph is a node link diagram that you see here. Now if the entities contain additional scalar attributes, we talk about an attributed graph. And here these attributes are shown by coloring the nodes according to some color map. So let's say the nodes in this graph represent persons and their connections, for example, represent family relations like parent-child relations extracted from a genealogical database. Then a typical attribute to visualize would be the person's year of birth. Now the analysis of such attributed graphs typically follows two main objectives that we need to take into account in a visualization. One is the analysis of its topological structure. In this example, an interesting feature might be the fact that this graph contains a topological circle. And typically we support the topological analysis by using a suitable layout for the graph. So the layout we see here might not provide the best possible comprehension of its structure, but other layouts like force-directed layouts, for example, can produce a node arrangement that much better reveals the structure and clearly shows such circles, here even without any edge intersections. Besides the topological aspect, we often also aim for an attribute-based analysis of the graph, for example to assess the overall attribute distribution or to perform relative attribute comparisons between nodes. Now the problem is that in general the topologically structured layout shown here does not inherently favor an attribute-based assessment, because even when using color-coded nodes like here, it is still hard to mentally infer its overall temporal structure. To support this attribute-based analysis, we would therefore rather favor a layout that orders the nodes by their attributes, for example in a linear or in a radial layout. A usual approach for our graph here would be to arrange the nodes along a timeline and perhaps use additional grid lines to support the localization of the nodes on this timeline. Now this layout makes it much easier to assess the temporal node distributions or perform relative age comparisons, but again diminishes the topological overview, as we have now in this small example already introduced an edge intersection again. So we see that in general an attribute-based layout conflicts with the aims of a topology-oriented layout, which becomes a problem when analysts need to combine these two objectives. In our work we aim to solve this conflict by combining a topology-preserving layout with an inferred contextual attribute landscape, which we illustrate as an underlying topographic map. We call such a map a topographic attribute map, or short a TAM. And in such a TAM, attribute values at nodes map to height values, which we interpolate to obtain a continuous height field. And by visualizing this height field using isocontour rendering, we can re-establish the relative comparability of node attributes that was before given by the grid lines in the linear timeline layout. For example, we can now again directly see the age difference between Joseph and Caroline, which is about 40 years, while we still preserve the topological structure of the graph. Now let's have a look on how we compute such a TAM. In the first step, we obviously need to define a layout for a node link diagram. That formally just means that we need to define an embedding that maps each node to a point in the 2D display domain. In the second step, we compute a height field that interpolates these attribute values at the node positions. In practice, we store this height field in a raster image of a certain resolution that encompasses the bounding box of the graph. And this height field is first initialized by rasterizing the node attribute values to this image. And then, based on these initial constraints, the remaining image is filled using a particular scattered data interpolation technique. In our work, we have investigated two state-of-the-art techniques, hierarchical diffusion and natural neighbor interpolation. Both are valid options. They both produce a smooth height field that interpolates the attributes at the nodes. They only differ in the exact shape of the landscape they produce. Then in the third step, the height field is rendered in the style of a topographic map. That means we map attribute values to a discretized or a banded color scale and show isocontours of the height field and apply Lambert shading to obtain a three-dimensional appearance. And finally, we also place height indicators onto the map. So here we start from some random seed locations on the map and then follow the integral curve of the gradient field and place a height label wherever this curve intersects an isocontour boundary. And in the last step, the node link graph is rendered on top of this map using node labels or other additional overlays that you might need for your graph. Additionally, we also allow for interactive highlighting of isocontours to foster explorative or comparative analysis tasks. Now, in the following I want to address two specific details on our algorithm that extend this basic computation pipeline. The first one addresses the visual embedding of the graph in the height field. So suppose we have this section of a node link diagram here that involves multiple smaller and a few larger backbone edges. Now, if we interpolate the height field based on the node constraints alone, then the resulting landscape does not quite reflect the topological structure of the graph, which is often dominated by the longer edges. In particular, if we follow these longer edges from a lower to a higher elevation, does not represent a monotonic ascent, but has to overcome hills and saddle points. So to improve the overall visual embedding, we therefore initialize the height field with additional constraints along the links that linearly interpolate their end node attributes. And this way, the edges become more naturally embedded into the landscape and follow a monotonic attribute slope. Now, while this produces a landscape that visually much better supports the structure of the graph, using edge constraints raises a problem when two links intersect at a point where both have different interpolated height values. Here we see two such cases in the detail region of this graph where edges at a lower altitude intersect with edges at a higher altitude. So here the question is which height value to use at the intersection point when we initialize the height field. One option is to just average these height values, which leads to smooth saddles that we see here, but now actually none of the edges exhibit a monotonic change in elevation. So instead we use a more natural representation that aligns with our landscape metaphor. If we interpret these edges as streets that cross at different altitudes, then we have two options to define the landscape at the intersection point. Either we model here a trench that embeds the lower situated edge and route the higher one over it using a bridge, or we raise the landscape to create an embankment for the higher situated edge and route the lower one under it using a tunnel. In our work we chose the second option just because we found that tunnels have more distinctive symbols in topographic maps. So to realize this, we need to initialize the height field first with the maximum of all link height values at each pixel, and this creates such embankments when the height field is interpolated. And then when we render the graph overlay, we step along each of its edges and test the interpolated height value of the link against the height value of the attribute height field. This way we can distinguish between points on the edge that are above ground or underground. And we render such underground intervals using a common topographic style with dashes and tunnel glyphs to mark the entrance and exits. So this way we can achieve an improved visual representation of such link crossings. Now, to evaluate our visualization technique, we have applied it to graph data from different domains. In the first example, we have applied TAMs to a graph provided by researchers in edge computing. You see here a topology of 10 edge networks that are interconnected by an internet backbone node in the middle. And one of the goals is to reduce the overall data traffic by improving the resource allocation strategy. So ideally, computational tasks that operate on data should happen closer to where the data is stored in the network. Now this TAM here compares two different resource allocation approaches and shows the overall traffic volume they produce at each device node. So while on the left baseline method a lot of traffic is routed over the cloud in the middle, you can see that the optimized approach on the right heavily relieves the central backbone and concentrates the data movement at the edges of the network. Another use case, as initially shown, is visualizing large genealogical graphs. To this end, we have cooperated with 2 expert genealogists, and one of the datasets is shown here, comprising over 5,000 persons in about 1,700 families and reaching back to the late 16th century. On the global scale, you can see the ancestral roots in the deep blue regions or clusters of complex interrelationships that appeared here in around the 18th century, and also large circular connections that span 7 generations over a time range of over 200 years. So let's zoom into one of these regions to see the depth of this graph in more detail up to the individual families that we show here using red circles. Finally, I want to note that our method is applicable to other graph layouts as well. So here we see, for example, 2 TAMs of the family tree of Marie Antoinette, once using a forced layout and once as an H tree. And in the paper we also show how we can modify forced layouts to gradually obtain a more attribute ordered layout. For this and for other extensions, as well as a report on a user study, please have a look into our paper. Thanks for watching.